How about now? Can you hear me fine? Okay. You just try. Okay. So, all right. Today I'll finish up what I was doing from last time. So I'll talk about compactness and gluing and how this is actually a complex and has the right properties and whatnot. And first I'll start off with that, and then I'll move on to some examples and some topological constructions that allow us to get whatever hypothesis we had imposed. And so then we'll be able to talk about any three manifold, not just integer homology spheres. Okay, so just a brief recap from last time. We first had a hypothesis which was the following. The Chern-Simons functional on the space of irreducible.
Can you recap from a little further back?
Oh, I was.
Okay.
Okay. Yeah, I think I was going to sort of build up all. Yeah, I just wanted to start off with. Okay, we talked about what Chern-Simons being Morse meant.
Okay.
Yeah. So we have a Chern-Simons functional on the space of configuration of connections. I mean configuration space of connections. So that's, I'm putting the star there just to say that we're only dealing with irreducible connections throughout. And so this is Morse is what we had said. What that meant was that if A is flat, then H0 of A equals H1 of A was equal to 0. So H0 of A basically meant that the stabilizer is zero dimensional. So that's what the irreducibility condition is. And H1 meant something slightly more, and it meant that essentially that this thing had Hessian that was invertible. Okay. All right. So that was what that was how we ensured that thing was Morse. All we did was we asked the hypothesis itself to be that all critical points have non-degenerate Hessians. Okay. So, do you want me to go further back?
No, I'm just saying. So, can you say what BE is? BE is
the
space of SU2 connections, or sorry,
connections
on an SU2?
It's irreducible SU2 connections quotiented by the gauge group.
Okay.
Yeah.
And E is a fixed SU2 bundle or a fixed three number?
Yes. So Y is an integer homology sphere. I think I had that later on in the notes, but I can state it here as well.
And E is an SU2 bundle.
The only SU2 bundle over this is the trivial bundle. Oh. So yeah, E is the trivial SU2 bundle.
Trivial SU2 bundle.
Yeah. Okay. Yeah. Okay. Now let theta denote the trivial connection. Connection. Then we said the sort of kth chain group was the free abelian group generated by A flat and K congruent to GR, the grading from any path from theta to A mod 8. So what I mean by that is take any path of connections from theta to A. You can talk about the linearized ASD operator on this, and you can compute its index. And that index is going to give you an integer, and K is just going to be that integer modulo 8. And
so for this thing also, do you need homology sphere, because otherwise the trivial connection will not.
No, the trivial connection will always exist, and you can always take. So you're right. If you do need a homology sphere, because this thing will this formulation will cause some issues if A is not irreducible. Yeah. So you're right that on this whole cylinder you need irreducibility at some points at least. Yeah. Okay. And the differential, how we had defined it, was the coefficient of D, the coefficient of A plus in the expression for the differential of A minus was just the count of union of B's with A minus, A plus, Z such that GRZ A minus A plus is equal to 1. Okay. So this is where we had stopped last time. Now, immediately a question you should have at this stage is, why is this union finite at all? Right? There is, a priori, there is no reason for this thing to be finite. I mean, in the finite dimensional Morse theory also, this was a question and just swept it under the rug. But now, since the finite dimensional case was only an analogy, I need to prove this from scratch. Okay. So, so to set that up, let me say a little bit about what space this Z lies in. So Z lies in the connected components of the path space from A minus to A plus. So these are just all paths that are asymptotic to A minus on negative infinity and A plus on positive infinity. And so this is isomorphic to BE. So paths of the interval 0, 1 with starting endpoint A minus and with the starting point A minus and with the endpoint A plus. So you don't need to worry about BE or BE star over here. It will not affect a computation of phi 1 at all. Okay. Now, so that's good. Now, again, abstractly, you can say that this is isomorphic to BE, where both the endpoints are same. So just pick some A that's irreducible. Then it's isomorphic to that, and this is a fact that this is actually isomorphic to the integers C. So potentially this could be an infinite union. All right. Now, so, okay, let me put the finiteness question in as the following two questions. Are there finitely many Z with non-empty moduli space? And the next question is, for the non-empty ones, are there finitely many?
So just conceptually, why is that Z? I mean, for instance, what is the generator?
Oh, yeah. So BE is AE mod GE. So what that, since A is an affine space, so it's contractible. So that means that pi 1 of BE is isomorphic to pi 0 GE. Now, yeah, okay, let me spend a little bit of time on this. This is worthwhile. Okay. So now you have, now GE, since E is the trivial bundle, just corresponds to maps from your 3 manifold Y to SU2. Okay. And just as far as homotopy groups are concerned, you can think of SU2 as just a 3-sphere as well. And you're just looking at maps from, so this is just pi 0 of maps from Y to S3. Now your classical differential topology kicks in to say that, okay, you have a map between two closed manifolds of the same dimension. So their homotopy class is classified by the degree of the map. And so that degree is what the integer is supposed to be. And so to be even more explicit, given any three manifold, what you could take is take a small point outside. So you have some, okay, you have some three manifold, you have some small point, and you take a ball over it, and then you could just uh, collapse everything outside of this ball to a point. So what you have then is this collapsed to a point, and so that's the cone on some ball. The cone on, yeah, you take a ball, take its boundary, cone it off, and that's an S3. And this map is going to have degree 1. So yeah, that is what the sort of Z is for that. So yeah, that's why it's a Z. And yeah, there are a bunch of these isomorphisms that keep going around. It's once you unravel them, they're pretty elementary, but unraveling them takes a bit of time.
I mean, at the level of connections, what does that map correspond to?
So take a connection, take a map G which has degree 1. Take the pullback of this connection under this gauge transformation, connect them up by a path. So this is going to be a loop because you're identifying connections that are gauge equivalent, and this is a non-trivial loop. Yeah. Yeah, I mean, this is a lot of it is just chasing down isomorphisms in this long exact sequence of homotopy groups. So, yeah. So.
So here Z is varying over paths between A minus and A plus. Right?
Yeah, little z is varying over paths from
Components.
Yeah, over components of
Components,
paths. Yeah.
components of paths between these. So are you only looking at those paths which have formal dimension 0? Or
Yes, I'm looking only at those. So I think I'll set this at yeah, this thing formal dimension 1.
Okay.
So the
Yeah. So that
yeah.
depends on the path that formal
Yes.
dimension 1.
Yes.
And then after rescaling 0.
Yes. After modding out by reparameterizations, it's 0. Okay. And all right, now let me state an assumption that we'll have throughout for today. All M check plus are transversely cut out. By that, what I mean is that this linearized operator restricted to the moduli space from is surjective everywhere. So whenever I say formal dimension is something, that means that this moduli space is a manifold of that dimension, right?
Can you just remind us what F was?
Oh yeah, F was the ASD. It was this thing, something like D. Sorry. A plus, and then direct sum, there was this gauge fixing condition. A minus A naught. Yeah. All I meant is that whatever equation defines your moduli space is actually, it's 0 set is transverse. Right? Yeah. So this is slightly stronger than assuming just that these are manifolds of the expected dimension, because that happens even for things like clean intersections, but we're asking it to be actually transversely cut out. Okay. So with that standing assumption always in the background, let's talk about this finiteness issue. Okay. Call that. So this has to do with this thing called spectral flow. Okay. So how do, let me tell you what it's defined as. So spectral flow, which maps from pi1 of PE A0, where A0 is irreducible. C is defined by just take any part Z and then compute what this number is. Okay. Now, I want to point out that in finite dimensions, whenever you try doing something of this sort, if you try doing any spectral flow of sorts where you say, okay, you have two critical points, you take a path and look at the index, they will always be a trivial homomorphism. And the reason for that has to do with, so okay, we had dA and we said that spec dA was equal to, I mean, it went all the way until minus infinity, and then there was until 0, and then there was some positive eigenvalues, right? The point is that both positive and negative, there were infinitely many eigenvalues. In the finite dimensional story, you will have only finitely many negative eigenvalues, I think. So what that leads us to is that if you look at just the space of all Fredholm self-adjoint operators, this splits up into three things. One is unbounded eigenvalues. That's the first component. Then there is essentially positive. What that means is that there are only finitely many negative eigenvalues. And then another is essentially negative, which means there are only finitely many positive eigenvalues. So the point is that this has some non-trivial topology. This is in fact homotopy equivalent to BSU infinity. Or is it B? Yeah, it's BSU infinity, I think. And these are contractible. So in the finite dimensional setting, you'll be either in one of these two, and both of those carry no non-trivial topology. But this one carries some topology. So there is some hope for this map from pi1 of BE to A0 to BSU infinity, and then taking pi1 for that to be a non-trivial homomorphism. Yep. No, this is not BU infinity, S infinity. One sec. It's the looping. It's U infinity, in fact, I think. Yes. Yeah, sorry about that.
So these were Fredholm operators on this SU.
Just Fredholm operators from some separable Hilbert space to itself. Yeah. Yeah. I mean, if this comment didn't make too much sense, it's fine to ignore it. I just wanted to point out that this phenomenon of spectral flow that you're seeing, the reason it's not discussed anywhere else is because it does not appear anywhere else. I mean, it does appear in other Floer theories, but yeah, goes by different names in that context. Okay, so this is the map, and the point is that using Atiyah, Patodi, Singer index theory, what you can show is that SF of Z is just going to be 1 over pi squared integral trace of FP wedge FP over R cross Y, where B is just a path of this form. This AT, where with AT equals A0 if T is much greater than 1. Okay. So if that happens, then this is to define it. What you should first notice is that since this is just 8 times a sort of Chern class, this is always going to be 8 times an integer. Okay.
So this condition seems to be stronger than this asymptotic to 0.
Oh yeah, but it does not matter. The reason I'm putting it that way is that I'm thinking of the fundamental group as like loops on the interval. But you're right, even if you just had asymptotic control, as long as the decay was fast enough, this definition still makes sense. The only point is that it should reach a naught. If it reaches a naught exponentially fast, for example, it's good enough. Yeah, and that will essentially be guaranteed in whenever your critical points are non-degenerate. So, but I didn't want to talk about a naught being a flat connection that's non-degenerate and such. So that's why I stuck to this simplifying assumption. But yeah. Okay, this is one thing that we have. Another. Okay, we can remember that our Chern-Simons functional was B to R mod Z. So we can ask what this does at the level of pi 1. So we have pi 1 of CS, which goes from pi 1 P to Z, which is pi 1 of S1. And the fact is that this can be checked with all the identifications that I gave. It's that this is an isomorphism. So put that in brackets. So this is an isomorphism. So what that means is that sort of upshot of this observation is that spectral flow is 8 times the homomorphism defined by the Chern-Simons functional. The important point is not that the factor is 8, but that it's a positive multiple of the other homomorphism. Okay, why have I emphasized this? So let me just quickly show that how there are only finitely many Z for which the moduli space is non-empty. So that's going to be as follows. So suppose Zi is an infinite sequence in pi 1 BE with endpoints A minus and A plus. Then first of all, what we can do is we can pick a canonically chosen path.
Sorry, just to interrupt. This the map pi 1 CS. That's essentially just the second Chern class, right?
Yes, yes.
That's essentially the definition of the second Chern class. Right?
I mean, essentially, the point is that once you have this thing, you have like a bundle on y cross S1, and you take the second Chern class of the bundle over that. Yes. Yes, and so that was why I wrote 8 times C2 within quotes. So that C2 was supposed to be C2 of the bundle over y cross S1. Yeah. Okay. All right. So suppose we had an infinite sequence of paths inside this thing with moduli spaces that were non-empty. Then I'll show that we reach a contradiction. So first, what you can do is you can just pick a canonical path from, not canonical, but you can choose a preferred path from A plus to A minus and close up all of these things to get loops. Is infinite in, now it's just going to be BE with A minus and A minus. Just because you have concatenated a short path from A plus to A minus. So now if this is an infinite sequence, because of the Chern-Simons functional being an isomorphism, what this means is that so evaluating that on the Zi tilde, this goes off to infinity. What that means is that because the spectral flow is like a positive scalar multiple of that, you get that spectral flow also goes off to infinity. And this implies that the relative grading along the original path Zi this goes off to infinity. And we had asked for there's a contradiction because we'd asked gr zi of a minus to a plus being 1. And so this contradiction tells that we have only finitely many zi's that get the job done. So essentially what I've used implicitly over here, I mean, now you might ask, okay, why can't we just say there's only one value, one path for which this is non-empty? And the reason for that is going from here to here, we adjoined some finite path, right? To turn them all into loops. So that correction term will be some finite quantity. So that's why if it's going off to infinity, that does not affect the argument. But if it stays at some finite place, then this can change the value by some finite amount. And so you can't conclude that there's only one loop, one component of the path space for which it's non-zero, I mean non-empty, but there's going to be finitely many nonetheless.
So are there examples where there is more than one path?
Can I tell you an example off the top of my head? Not that I don't have one off the top of my head at least.
But they're likely to exist.
Yeah. Especially when you perturb and stuff, I don't think you have any reason to hope for any control. Yeah.
So can you just go back to definition of SF?
Oh yeah. Yeah, so SF was supposed to be GRZ of A0 to A0.
It's the gradient.
No, so this is the grading. So it's like if you look at the moduli space of connections from A0 to A0 itself, then what is its formal dimension?
Okay.
Yeah, this is the formal dimension.
Then you have used some Chern-Way kind of expansion.
Yeah, I mean, I've used Athiya Patodi Singer to tell you that it's given by some Chern-Way expression, but yeah. So I guess I should mention that over here for using the APS theory, we have again implicitly used the fact that we're on an integer homology sphere. But that's of not much consequence in the most general case also, but just wanted to point that out.
The other thing about your statement of Fredholm is those are the three connected components.
No, there's just, sorry, it's just, yeah, all of those are going to be components, and the point is that this is a decomposition of Fredholm operators, and two of them don't have any topology, but one of them has all the topology. Yeah, I should mention that this is for self-adjoint.
With what topology on the space of operators?
Just your operator norm, like just your operator topology. Yeah, these are self-adjoint. I mean, the reason for asking it to be self-adjoint is only then can you make sense of essentially negative and positive. And yeah.
Is it single or bunches of components? Because I would think spectra going off to infinity at different speeds or something.
Oh yeah. I mean, so I guess I should really say these are
of these three forms, and all components that are essential positive and essential negative, I assume, are contractible. While
yeah,
the other ones.
I think these are connected. These are actually connected, and this one might. This one also is actually connected because you're shown its homotop equivalent to U infinity. Okay. But you're right that it's a non-trivial fact. Yeah. Sorry, should be
yeah. So, assuming some kind of additivity of the grading, right? So is that like from the gluing theorem?
Yeah. That's from a sort of linear gluing result, which is. I mean, basically, whatever tools you use to prove the Athiya single index theorem, some of those tools can be used to say that if you are gluing things, then at least at the level of differential operators, they do the right thing. So you're right, I'm using that. So that's why I'm able to say, for example, things like if I had this as an infinite sequence, then I got to this thing and got to this, and I was able to use this to gain control over this quantity because of the gluing result. Yeah. But the gluing result, at least at the linear level, the gluing result is not supposed to be anything too sophisticated. It's supposed to be, it's the first thing that you think of, and it turns out it works. Okay. Right. So, and yeah, I guess just another point for anybody who has seen Morse-Novikov theory. So you might be wondering, why am I able to do everything over the integers and not have to deal with these Novikov parameters and such? And that also has to do with the spectral flow argument, essentially. The point is that since you can't have infinitely many loops that show up, you don't need to keep track of the energy with the Novikov parameter. But anyway, if you have heard of Novikov-Morse theory, that comment made sense. If you have not heard of it, it's all good.
So that's something that's in the symplectic side, right?
Yeah, it's on the symplectic side, and it even happens at the finite dimensional level. Like, okay, I mean, this is a bit of a digression, but let me talk about it anyway. So you have this function from S1 to S1 just being identity, right? Now, if you try computing Morse homology from this, what you will conclude is that so S1 with F, the Morse homology, this is just 0, you'll say, because there are no critical points at all. And so the real way to do this is to say that when you have any S1 valued function, you need to introduce this sort of Novikov parameter. And in that, what will happen is, say you had your usual thing with 2 critical points, right? So then you would have something like CT plus or minus 1 to ZT plus or minus 1. And then I think this will be this in this Morse in this Novikov setting, this will turn out to be, if I'm not mistaken, it will turn out to be this, I think. And so now this is an isomorphism. So the kernel is empty, the co-kernel is also empty, and so you recover that. But this is not your usual thing.
I guess the elementary point here is that you're looking at circle valued Morse functions.
Yeah.
Your CS is also circle valued, and so that you will Novikov Morse.
Yeah, so you would.
Finite dimensional, so long as it's a circle valued Morse function.
Yeah. So a priori, when you're working with a circle valued Morse function, you'd need these Novikov parameters or something, but somehow magically for us that does not happen. Yeah. So in the symplectic side, in fact, this is unavoidable, and this does show up as yeah. Let me just get rid of this because this was not supposed to be too serious of a digression. Okay. Finally, compactness and gluing. Okay, so we'll show both that this cardinality is always finite and that d squared equals 0. That is, well, yeah, let me just say what that means later on. So the key result in sort of thing is due to Uhlenbeck and Dobbs. So they come at various spots. So rather than being very careful about the attribution, I'm just going to say that everything covered in this part, this section is goes back to work of Uhlenbeck and Dobbs and various other folks. So given any connection on R cross Y, we can just talk about its energy. So this is just, we are assuming that the limits of this are flat, so that this expression is even convergent. And we ask for all our connections to have energy at most 1 for all A inside. So some equivalence class A inside, check of A minus A plus. Okay. And we also assume A minus not equal to A plus space. Okay. Then this can be compactified to M check plus with C, which is now which is a stratified space with co-dimension 1 strata the union long A naught of M check C minus used to be naught cos M check C plus A naught A plus. Okay, so let me just put this a little there. So the result is that once you have like a uniform bound on the energy of all these elements, then you can actually compactify them into a topological space, which is going to be a stratified space. And we also know what the codimension 1 strata is going to be. So if this were, in particular, if this were a 1 manifold, then the compactification is a 1 manifold with boundary, and the boundary components are that.
And in your case, it's a 0 manifold, there is no boundary.
Yes, yes. So
It's
indeed.
finite because it's compact.
Yeah, so I mean, if this were 0-dimensional, then first of all it's discrete, and because of this result, it's going to be compact, just because all of the strata is going to be empty, and so that tells us that it's a finite thing. So that tells us why our that already sort of gives us this property, and this property is going to correspond to that the one-dimensional thing can be compactified with boundary components, and the boundary components can again be seen as the boundary components can again be seen as these sort of broken trajectories. So this is, you should keep in mind exactly the finite dimensional Morse theory picture where you had something like you had two broken things and you wanted to say that nearby there was something like this. So that's how this decomposition also comes about. But there's one thing to be noted, which is that in this statement, nothing is said about whether A naught is irreducible or not. So to make sure that our differential does actually square to 0, we need to ensure that nothing in this has A naught being the trivial connection. Okay, so let me write that as a claim. The claim is the following. If A minus and A plus are irreducible, then with the relative grading or the relative index being less than 3, then A naught is not the trivial connection. So how does the proof of this go? The proof of this is that the additivity of this thing is now changed a little bit. So it goes as follows. We have naught plus dimension h is 0 plus dimension h1a is equal to grz of A minus A plus. Okay, so So we need to only worry about the cases when these things are non-negative, because if they're negative, then because of the original transversality assumption, that means we have a manifold of negative dimension, so it must be empty. And so we only care about those cases. And now already dimension of H0 of theta is going to be 3. That's just the dimension of SU2. And so since this is less than 3, that will force some of these things to be negative, and that can't happen, and so we have a contradiction. So A0 could never have been I should say A0. So A0 could have never been the.
Where did we use the fact that A0 is not trivial?
So if A0 were trivial, then this thing is going to shoot out these terms. So I guess I should say it this way. So I talked to you only about this
I see. So
relative.
the dimension is 3 is where you
Yeah. For the trivial connection,
Right.
it's 3. Yeah. So there is a small caveat, which is that I talk to you about these terms only when everything inside is irreducible. So something more needs to be done when some of these things are reducible, and which is, I mean, if you've heard of it, it's like adding exponential weights to ensure convergence. Morally, what's happening is your whatever Fredholm problem is not being Fredholm, so you force it by saying, okay, you ask for everything to die near infinity, and that will somehow recover Fredholmness, and you'll be good to go. But yeah, anyway, I wanted to point this out just for the fact that the only reason we've been able to ignore the trivial connection everywhere is because of things like this, because it's in some sense so isolated from the rest of the representations that it never interacts with them.
also yeah.
No, but again, what you said, reducible but non-trivial connections, are they there at all, or are they?
We're assuming integer homology sphere.
So they are not there.
Yeah, they're not there to begin with.
Yeah, so I also had a couple of quick questions on their compactness result. So firstly, I mean, this the trace thing is the second Chern class, right? But I guess all these things are AST, so you get an a priori bound in the L2.
Yeah. In fact, the a priori bound is going to look like this. This is for an ESD connection. This is just 1 over 8 pi squared, the L2 norm of A minus.
Right. And then, I mean, I guess then once you have an L2 bound, you have compactness. But also Uhlenbeck has, I mean, you have these singularities at these isolated points.
That's why we assumed this less than or equal to 1. That for a point to become singular, it needs to suck off at least 1 unit of energy.
I see. Because
so,
it has to be like some Dirac mass on some point, and so then you
essentially
have
yes. Yeah. So that's why I assumed this as well. A minus not equal to A plus. If they were, if this 1 unit of energy somehow got sucked off, then what remains has no energy. That would have forced the endpoints to have been the same. So you're right. And in fact, even going from this L2 estimate to compactness is not as simple because of non-linearity in the PDE. So,
right, but that's the Uhlenbeck.
Yeah, that is the Uhlenbeck compactness result. Yeah.
Yeah, because the way I have usually seen it is like Ln by 2 norm on the.
Yes. So yeah. So in general, if you had tried doing this with on an n manifold, then you would have had to somehow assume that you have Ln over 2
right,
control,
which is a very unnatural bound, except so
Yeah.
dimension 4.
Yeah.
Okay.
And then how does this energy less than equal to 1 show up in this case, our case? Like,
Oh, so in our case, the thing is that if it were equal to 1, what could happen is that beyond just these components, you could have, so instead of the cylinder breaking up into pieces, into things like this and such, you could have had a sort of bubble that shows up at some finite stage.
yeah, right,
And-
so that's automatically satisfied.
No, what I'm saying is because of this energy bound, that the energy is at
Right.
most 1, this bubble, whenever it forms, has to have energy at least 1.
No, I think maybe.
No, like this,
Why is that?
Yeah, why is
that hypothesis true in the logical?
Oh, right. Okay, sorry. Yes, that is a good point as well. So the reason is essentially because of this. That is going to ensure that, so because if you write down the index formula for this thing, the energy term shows up. And so because of that, you will be able to, this bound will give you an energy bound, and that energy bound sort of now feeds back into this compactness result. Yeah, that's a good point. I completely forgot to mention that. Yeah, so I should say this implies k less than or equal to 1. In fact, it'd be less than or equal to maybe even. Let me just keep it 1. It's probably better than that, but even more. Okay, here's a more concrete heuristic reason as to why this bound ought to be satisfied. So say there was this thing that escaped off, right, as a bubble. So this bubble could happen anywhere on this 4 manifold. So the introduction of a bubble, first of all, sucks off some amount of energy. So this turns out, in terms of dimension, it ends up sucking off 8 dimensions. And you can vary this point over any 4-dimensional space. So you end up with a loss of exactly 4 dimensions, like of 4 virtual dimensions. And so since all of our modularized spaces are going to be 0, 1, or 2-dimensional or something like that, you cannot hope to lose 4 dimensions and still end up with something non-empty. So yeah, that is the main sort of heuristic you should keep in mind.
8 dimensions because of that 8 times 12 class.
Yes, in the index formula.
Index.
Yeah.
On 4 because that's the variation. Anywhere it can be.
Yes. Yes.
Oh, so the spaces with bubbles are co-dimension 4 is what you're saying. Okay.
Yeah. Yeah. Yeah.
Because the bubbles itself drop 8 dimensions, but bubble anywhere adds 4.
Yes. Yes. So formal dimension 4. And actual dimension 4 also in some cases due to Dobbs's gluing results, where it shows that these things are still going to be transverse and everything.
Meaning their bubbles exist, but as far as
Yeah.
you are concerned, here
we are sticking with very
bubbles don't come back.
Yeah, here we're sticking with very low energy solutions, so these bubbles will not ever bother us. So yeah. Anyway, since we have now ruled out that these trajectory breaking cannot happen through the trivial connection, and also that there are no bubbles that come about, this proof of d squared equals 0 in the finite dimensional Moss theory case carries over verbatim to tell you that in our case also we have d squared.
The general question here, so this is in Fukaya and so on, you get cup product and Massey products and so on by looking at higher paths in Moss theory. Is there some stage where the dimension 3 is actually a problem here?
Yeah. So I told you that this one is only when this thing is less than 3, right? So what if I look at moduli spaces of dimension 4 or something? Then in fact it will interact with the trivial connection.
Yeah.
And this has been studied by Kim Frosho.
Okay.
And that's how we talked about these so-called reduced instanton groups that account for these interactions with the trivial connection, and they give you another flow group, and there is a discrepancy between these flow groups, which he calls the Frosho, which is called the Frosho invariant. He didn't call it that at his time. But
oh, you do get that.
Yeah. So there is you can deal with that as well. Over there again, the point is that if there's only one bubble coming, then there are gluing results. If there's more than one bubble, I think there are some partial results, but not quite all the way. But yeah. Yeah, I considered talking about that, but that would take me far too long to introduce it. Get things going, so decided to not bring it up. Okay, now that we have defined what these instanton non-flow groups are, we should first think about, okay, what are the examples that we can have with this, right? So again, the biggest class of examples is ciphered fibered homology spheres. So we just put that title. Ciphered homology spheres. So the main theorem is due to Instanton and Stern in their 85 paper. What it says is that, so let this be a ciphered homology sphere with n singular points, and it's a integer homology sphere. Then I sharp of y, sorry, not I sharp. I of y is a free red model concentrated in even degrees or even gradings, degrees or grading, whichever word you prefer. And in fact, if the irreducible representation variety is, say, you break it up into its components and say the components are R alpha, then is a direct sum over alpha of where nu alpha is a computable even integer. So what this says is that, in fact, the Instanton homology of y is just the homology of your representation variety with some shifts in gradings. So this is in fact how it morally arose as well. Like the point was to try to talk about the homology of your representation variety, but there is no canonical way to desingularize it. And in this case, you're lucky that all these R alphas are going to be rational varieties. So they're all, I mean, and the thing, the smoothness is not guaranteed, but nonetheless, we can still compute their homology. And it so turns out that this result ends up holding. And so
you've taken a ciphered fiber expression.
Yeah.
With A1, A2 indices of fibers.
Yeah.
And it's an integral homology sphere.
Yes, it's an integral homology sphere. Yeah.
So the base orbifold is necessarily a sphere.
Yes, a sphere with n marked points with.
It has to be an integer homology.
Yes.
Sphere.
Yes.
Why is that?
Because otherwise there'll be a B1 contribution just from the base orbifold.
Oh yeah, base orbifold is a sphere.
Yeah.
Not spherical, but a sphere. Yeah.
Yes.
It could be a hyperbolic orbifold, but a sphere as the
Yeah.
topological sphere.
Yeah. In fact, it will turn out to be hyperbolic once n is greater than or
Most of
equal
the
to
time.
3. Yeah. For n equals 2, I don't even think you can get an integer homology sphere. So, yeah. So Briescon homology spheres fall under this, for example. And yeah, I mean, Fintushel and Stern in their paper, they give like a whole table of particular cases that they've computed. But let me just tell you one computation over here, which is of the Poincare homology sphere. So sigma 235 is the Poincare homology sphere. And its Instanton homology is there's going to be 1 in grading 2, and then there's going to be another in grading 6. So they're basically just going to be two irreducible irreducible representations from the fundamental group. So that's just corresponding to the icosahedron group having two distinct embeddings to SU2. Okay. And so those are the two ones that show up over here. Okay. And so questions at this stage about the construction or examples, or if you want to, I mean, I can't be sure that I'll know all the answers for these examples, but if there's any other cipher-based homologies where you wanted to know the answer for that.
So they actually had to compute all these
Yeah, they had to compute these representation varieties. Yeah, but the point is, it's not as hard as it looks. It turns into some combinatorics because, sorry. So the point being that you have a very explicit description of what the fundamental group of these cipher fiber spaces are, and you can leverage that into saying that okay, there are some axes, and then that these form some triangles, and then you count how many spherical triangles there are and such. So for the case when there are 3 singular points, these you get triangles and they are rigid, and if there are 4 or more, then you get these sort of linkages, and these representation varieties turn out to be these moduli of linkages, which I think there is one algebra geometric way to understand it and also a symplectic way to understand it, I think. And but yeah, I mean, this is not to say that that it's easy, but like it's very tractable.
Yeah, so I think you said that all the dells turn out to be 0 just for
dimension reasons, yes.
So you only need to know the generators, you don't need to.
Yeah, you only need to know the generators because all the generators will have even or odd grading thing, and the point is the difference between any two generators is going to be even, and so there's no one-dimensional moduli space zero-dimensional moduli space that you'll need to count.
And the other thing I think you said was that the representations actually descend to the orbital group because of the lack of the center of SU2.
Oh yeah,
That's why you get spherical triangles.
Yeah, that has to do with just some you can call it, I guess, group theory or low-dimensional topology, but yeah.
I mean, just the fundamental group of cipher fiber
Yeah.
have a S1 being the center and the
Yeah. Yeah. Something of that sort, yes. Yeah, so in fact, the point is that these representation varieties are basically representations on the base orbifold. So they're like some K-punctured sphere or something. So you have some sort of, I mean, this is not quite, I mean, it is isomorphic to a free group, but not exactly canonically. So you pick the presentation by, like a loop going around each singular fiber that you have these representation. Okay. All right. How much time? Half an hour. Sorry. So let's talk about topological constructions that get rid of a lot of hypotheses that have been hiding under the rug throughout the discussion. But okay, so the main point of these topological constructions is to ensure that all flat connections are irreducible. As far as the other thing like Hessian being not degenerate and all the other things are concerned, those you'll achieve by a specific choice of perturbations. But the main point that causes issues is that if you try to use those perturbations naively, you could turn an irreducible critical point into a reducible critical point. And now you'll need to further perturb and you can't get any control. So what we'll try to do is we'll just try to ensure that anything that even is close to flat has to be irreducible. And that will allow us to perturb by small things so that irreducibility is never lost and all your moduli spaces and whatnot are transverse. Okay, so there are two variants. I mean, there's one main construction and then another sort of application of this main construction. So the first main construction is so-called admissible bundles. Okay. All right. So far we have talked about integer homology spheres, and the point is on integer homology spheres, any SO3 bundle lifts uniquely to a SU2 bundle. Okay. So now what we're going to do is we're going to actually deal with SO3 bundles instead of SU2 bundles, and we'll see how this helps us. Okay. So we'll first of all be dropping this integer homology sphere condition and be dealing with SO3 bundles. And so to talk about this, let Y be connected, closed, oriented 3-manifold. Then, so, and say E or Y is an SO3 bundle. Then we can build a fiber bundle whose fibers are the Lie group SU2 out of this. How am I going to build that? The point is the adjoint map from SU2 to group automorphisms of SU2, which is just going to be G goes to the function that's conjugation by G. So this is a group automorphism, and the center of your Lie group is going to be the kernel of this adjoint homomorphism, and SU2 mod center is as a Lie group SO3. So what this means is we have this adjoint map from SO3 to automorphisms of SU2. So this is what we're going to exploit to sort of go from SO3 bundles to sort of automorphisms that only look at, in some sense, the SU2 part of the bundle. Okay, so to be even more precise, what I mean is we can talk about this big adjoint bundle of E, which is just going to be take the frame bundle of E and do this twisted product construction via the adjoint map. So now what this means is that this is a bundle of Lie groups over Y, and all the Lie groups are just SU2. So what this buys us is that we can now talk about the gauge group as just sections or Y of this adjoint bundle. Now this acts on space of SO3 connections. So this is the key point. Like what you would have liked to say was that, okay, take the space of SO3 connections and take the space of SO3 gauge transformations. But that leads to issues just because the stabilizer group of SO3 that could show up would be SO2, O2, which are okay, but then there can also be the client 4 group, which is annoying. And so to not have to deal with this client 4 group and these unorientable sub bundles and things like that, you adopt this definition so that now your stabilizers are still sort of subgroups of SU2. And those can only be either the center or S1 or the whole thing. And yeah, I mean, if that didn't make a whole lot of sense, I'm happy to have an extended discussion after the talk. But for now, I'll sort of flow through to tell you like what, how this is. I mean, this is one thing that reduces the complexity of the issues that shows up, but I still not told you how to resolve the main issues that show up at all. So let me go about that. Okay, so we have this, and now, so now this E is an SO3 bonded, right? So it has a second Staffel-Whitney class, which now belongs to this with F2 coefficients. So F2 is just Z mod 2. And I'm going to be using that a lot. I'm just giving an abbreviation. Then there's this. Now suppose there exists a surface that's closed, oriented, sitting inside your 3-manifold Y with the following property that W2 of E evaluated on the fundamental class of sigma is not equal to 0 in F2. So all I'm saying is since this is a homological class, we get a homological class from the surface, and this evaluation has to be non-trivial. Then we claim that if is flat, then the stabilizer is just going to be the center of your gauge group, which is just 2 elements. It's just Y going to plus or minus 1. So how do I prove this? So now that this connection is flat, you have your holonomy representation mapping from the fundamental group of Y to SO3. Now suppose it did have some stabilizer, then what that would mean is that the image, this lies inside O2 at least. Okay. Now let's look at what the connection is when restricted to your oriented surface. So first of all, W1 of E restricted to sigma is just W1E restricted to sigma, which is equal to 0. So our bundle is going to be oriented. So what that means is that our holonomy representation is now not just going to lie inside, it's not only going to have image inside O2, it's going to actually have image contained in SO2, which is isomorphic to U1. Okay, so what that means is that E restricted to sigma with A restricted to sigma is of the form R direct sum L, where the connection is trivial on the R factor and it's some flat connection on L. So A tilde on L is flat. What this means is that so we can talk about the first Chern class of L, and what this buys us is that the first Chern class of L is 0. So let me rewrite that instead as implies first Chern class of L equals 0, implies W2 of E restricted to sigma is equal to 0, just because the mod 2 reduction of the first chunk class is what gives you the second Stiefel-Whitney class of L, and then you just use the sort of Whitney sum formula. But now this is actually, what this means is that W2 on E evaluated on sigma is equal to 0, which is a contradiction.
So assume sigma was an oriented surface.
Yeah, sigma was a closed oriented surface. Yeah. Yeah, embedded inside your 3 manifold, exactly, yeah.
But if your 3 manifold was a twisted I bundle over the Klein bottle over the Stone bottle, and
Yeah.
sigma was the Klein bottle, this argument does not work.
Yes, this argument would not work then. Yeah. Yeah, so this is under the assumption that you have a closed oriented embedded surface which evaluates non-trivially on the second Stiefel-Whitney class.
So you didn't use, where did you use the holonomy representation, that rho is it?
This, to say that it's flat. So to tell that the first chunk class of L is 0. The restriction of a flat connection is flat, and you knew that it was sitting inside O2. Now you know that it's actually sitting inside SO2. And yeah. I mean, essentially the point is that over your 3 manifold globally, there could have been a non-trivial real bundle that splits off, but once you restrict to the surface, that bundle trivializes. So yeah.
Already, I mean, because it lies inside O2, there will be a splitting even on the
3 manifold. Yeah.
But you're saying that that could be non-trivial.
Yeah, I mean, the real line bundle that stays there could be non-trivial. We don't a priori know it's trivial, and that's why Siddhartha's example of using the Klein bottle thing will not work as well, because when you do this restriction thing, that thing could still persist in some sense.
A real bundle will be non-trivial.
Yeah. And then what would happen? Then what would happen is that this D need not be non-trivial, but both L and this thing could have torsion, sort of, could have flat connections, but you know there'll still be some torsion element, and you won't be able to conclude things of this form. And so, yeah. I mean, I might be messing up a few points here and there, but the essential upshot is that you know what happens on closed oriented surfaces, but once it becomes non-orientable, then you're less, you can't run parts of this argument. Yeah. So yeah, the upshot is that, like, basically just on the basis of simple topological / Chern-Weil theory style arguments, you can ensure that none of the flat connections that show up are going to be irreducible, and also that small perturbations of them will also be irreducible, because irreducibility is an open condition and you can find uniform bounds on them regardless of what else you do. And so what you can do is that whenever all of these conditions are satisfied, you can define I star omega of y, where omega is one manifold closed, such that W2 of E is Poincare dual to class defined by omega. And we assume that basically there exists a closed oriented surface sitting inside Y such that this is sigma is odd. So whenever this is satisfied, you're good to go. Okay.
So in a homology sphere, your omega will be empty.
Yeah, in a homology sphere, there is no W, there is no H2 to even talk about a non-trivial W2.
But what about rational but not integral homology? Again, you will be.
There you can sometimes come up with these surfaces that get the job done.
So then Poincare dual with
F2 coefficients.
Yeah. Okay, so rational homology still has an upper one non-trivial.
Yeah. No, H
H
upper one is going to be 0. H lower one is going to be non-zero.
Not zero.
Yeah. So that's what affords you this luxury.
Okay.
Okay. In the last 10 minutes, I'll just talk about the last topological construction that I had in mind, so that after this we can talk about instanton homology of any three manifold whatsoever. And this is about connects.
Again, just a small point here. So
Yeah.
as long as it's a Z mod 2 homology sphere, everything is fine, right? It doesn't actually have to
No, as long as it's a Z mod to homology sphere, what it says is this trick does not work. So unless you are, if you have a Z mod 2 homology sphere that's not an integer homology sphere, then you're again in trouble. You can't
Okay.
talk about your thing.
No, I'm saying it's a rational homology sphere
Mm-hmm.
and H1 has only odd prime torsion
Yeah.
elements, then that
This trick does not work.
it does not work. Okay. So
Yeah.
then W2 will have to be 0, right?
Yes.
Yes.
And so now you could have reducible flat connections.
Oh, you could have reducible flat.
Yes.
Okay.
Yeah.
So what is the condition under which this works?
When you have a closed oriented surface along with this omega such that their intersection is odd.
Ah, okay.
Yeah. So if there is no two torsion, this intersection will basically, I mean, this intersection you're supposed to take in with F2 coefficients throughout.
Wait.
So if your F2 homology and all of those make it look like the sphere, then this thing is going to give you the answer as what you would get in a
You need
sphere.
sigma to be oriented.
Yeah, you need sigma to be
So
oriented.
it's some sort of a lifting of W2 that is.
Yeah. You want an integer lift of W2 in fact.
Okay.
That's what you really
Sigma will
want.
give you an element.
Yeah.
Orientable surface will actually give you an integer.
Yes.
Okay.
Yes.
So W2 can vanish if it's a integral homology sphere, otherwise it has to have an integral lift.
Yes.
So we don't like number theory.
Fair enough. That's one way of looking at it, I suppose. Okay, so like we already just had a brief discussion, we might not always be able to find such a sigma. So what's the way out? Let's force it. So how we force it is just connect some 3 torus, right? And our SO3 bundle is just going to be this, and I'm going to write connect sum to mean sort of like a Whitney connect sum sort of operation with E delta, where so now E delta is bundled over T3, and it looks like R direct sum L topologically, where the first Chern class of L is Poincare dual to delta, where delta is a coordinate circle in T3.
Do you want to rank 3 bundle?
This is rank 3. L is a complex line bundle. Yeah, and it's Poincare dual to this. And now this means that you can take this to be the span of the other 2 coordinate circles. So this is S1 cross S1. And now both of this intersect in one point. And so you have found a surface that gets the job done. And so you can just now define this to be, so you can, this is usually called sharp of Y, and yeah, this is defined to be I delta of the earlier construction of Y prime, and this ends up having a true periodicity property. So you allow star to vary only in 0, 1, 2, and 3, and not 4, 5, 6, 7, because those are going to be, 4 is going to be isomorphic to 0, I think, and 5 with 1, and so forth, or it's the other way around, I forget. But yeah, so you can talk about I sharp of this, of any tree manifold that you feel like. I want to just make another comment about this very unnatural looking construction has a very nice topological implication, which is that, so I'll just state this as an observation. So suppose you were lucky and you didn't need to perturb anything, and you look at just the critical points and whatnot. Then let's say the critical points are R sharp of Y. Then this, because we have eliminated the 2 periodicity bit and some other factors, this is just homomorphisms from this to SU2. So you're now no longer modding out by conjugation. So this is at least hopefully less singular than your representation variety modded by conjugation. So in fact, just using this observation, you can show that I sharp of S1 cross S2. So in that case, this is just Z, and so the homomorphism is just going to be SU2. So it's just a 3-sphere. So you expect it to be, rank 2 free Z module, and that is indeed the case. The grading is going to be concentrated on 2 and 3. So if you try using the earlier construction directly for S1 cross S2, where you pick a W or whatever, you'll get 0 over there. But now we have some non-trivial thing. That said, you should be cautious in the sense that even if pi 1 were non-trivial, it could so happen that I sharp is actually just rank 1. In fact, let me be even more precise and say, so here for one moment I'll be switching to complex coefficients. So if you just take the Poincare homology sphere, in fact, with complex coefficients, then this is just rank 1, I think, in grading 0. I might be wrong about the grading, but it's just going to be rank 1. So it looks like that for S3, because for S3 also this Hom space is just going to be a single point. So yeah, so while I sharp does sort of try tell you if there are homomorphisms or not, you can't detect non-trivial. You can't detect if pi 1 is trivial or not just based on I sharp. So yeah, with that last word of caution and then today's talk.
Just one point is that connected sum, because of Wilmer's theorem, if two manifolds are different, their connected sums will be different. So
Oh,
it's
yeah.
safe to take connected sums, unlike four manifolds.
I see. What is the theorem again?
So
For tree
prime
manifold?
decomposition. The
Oh.
theorem tells you prime decomposition is unique.
Is unique, yes.
So in particular, if you have this is an invariant. I mean, you lose no information by taking connected sum with T3. If manifolds are different. Oh,
Is
even the
T3
other way
prime?
is trivial.
Is T3 prime?
T3 is
Okay, right. Yeah, then you're right. The prime decomposition theorem due to Milner tells you that it's unique. Yeah. Yeah, but you should think of the connect sum device really as trying to remove the conjugation action over here, and hopefully get at something that's, if not Morse or Morse bot, to already begin with. And Fintushel and Stern got lucky that even modulo conjugation, that thing happened to be Morse bot. But now we're saying, okay, even if we're not that lucky, we can ask for this, and this typically is Morse bot. And so you can then say that, okay, I sharp is morally just supposed to be your Morse bot homology on this of this thing. And so in one particular upshot would be that you have a spectral sequence from homology of sharp of Y to which abuts to I sharp of Y. So, which you would not have had in the earlier context at all, just because there was not much hope of this being Morse spot. Whereas over here, typically you're able to make sure that it's Morse spot. Yeah.
Why does conjugation go away when you take connected sum?
Right. So the point is that if you look at this sort of Hom pi1 of T3 with SU2, but now you'll need to impose certain restrictions that corresponds to W2 blah 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 is equal to delta. You impose these conditions and you take conjugation by SU2. This has exactly two critical points. So there is this, and then there is, let me say, star prime. And there is a sort of involution that exchanges the two. So what you do is this involution is what sort of gives you the periodicity. So when you consider only the grading 0, 1, 2, 3, what you're doing is you're essentially looking at only things that correspond to one of the 2 points that you got.
But R sharp, I thought R sharp just meant the representation variety of Y without any reference to W.
Yeah. So what I'm saying is that
where does W2 even?
Yeah. So R sharp of Y is really homomorphisms from pi1 of Y prime, where Y prime is Y connects some T3 to SU2 with some conditions about the W2 on Y prime.
Oh, the conditions part,
Yeah.
Okay.
That's why we stuck with SO3 bundles. Like these restrict what homomorphisms into SU2 are allowed.
Oh, I see. Okay.
And that part, because of you can use Van campaign and see the user connect some decomposition to tell that what the splits up is as Hom of pi1y to SU2 with no conjugation. And then you sort of take a product by this whole thing. So the conjugation action is only on one of the 2 fundamental groups. And you sort of import all the conjugation to this one, and this one has this nice property. And so since you stick with only one of these 2 things, you get that, okay, this is actually what you get back is the full homomorphisms. So yeah, it's a clever topological trick to get rid of the conjugation action.
You have taken a particular bundle on this.
Yes, I've taken a particular bundle. So this delta is like a coordinate circle in T3.
And the trivial one on the right side.
Yeah. Essentially.
This sort of trick doesn't work. You connect some with S1 cross S2 or something like that.
No, if you tried S1 cross, so let's see. If you took S1 cross S2 and took some non-trivial W2, right? Then I think there are no flat connections at all that satisfy the constraint. There is another trick that you could do, which is, I think, I'm forgetting what it is, but there's another 3 manifold that you can use as well, I think, and try doing something similar. And conjecturally, they're supposed to give the same thing, but it's just so that in the literature, everybody has been using the T3 case. And so that's what's been standardized now. But yeah, there is another moral 3 manifold with a bundle over it that you can connect some as well.
So far, Instanton flow seems to be useful in classifying these homologies, integer homology sphere. Is that right? I mean,
It tries to do, yeah, I mean, it gives you more information about them, yes. Yeah.
Bounding 4 manifolds.
So it's also coordinates.
Yeah. I mean, like if you had like an integer homology cobordism from one integer, so say you had y and then you had say you had y1 and y2 over here, and this thing homologically looks like a cylinder, say, or looks like S3 cross I. So y1 and y2 homologically look like S3. Then you can quotient out by such relations and form this so-called this cobordism ring of integer homology 3 manifolds. And these instantons by themselves are not invariant under such changes, but you can extract numerical invariants out of them, which are invariant under such changes. So you get some sort of homomorphisms from, you get some homomorphisms from this to Z or F2 and things like that. And using things like this, one can show that this sort of group of integer homology cobordisms is, I mean, it's abelian by almost by definition, and it's going to be infinitely generated, example. And ciphered homology spheres don't generate it, but hyperbolic three manifolds do. Integer hyperbolic, like, yeah, closed hyperbolic three manifolds that are integer homology spheres generate this thing.
This previous theory, all that was known about that is that Rockland invariant tells you there are at least two components, right? Not yet.
That is subjective, that it has at least, that is a non-trivial group. Yes, that's all it told you.
Just Poincare homology sphere and
Yes.
F3 are different by Rockland
Yes,
invariant.
yes.
While Poincare homology sphere, which itself already needed Donaldson's theorem.
Yes.
That probably will come from Floer homology.
Yeah. I mean, like what I mentioned about Kim Froshaw, right? He systemized a lot of this Donaldson theory stuff to tell that all of that can be surmised from interactions of the irreducible connections with the trivial connection.
Okay.
And so that somehow tells you, I mean, I think it recovers all of Donaldson's things about, which things can bound three sphere, like which, what is the word? Quadratic forms, which quadratic forms can bound the three sphere and stuff like that.
Okay.
So,
Oh, okay.
Yeah.
Even the original one.
yeah, it gives you the original one. It gives you even more like things about the E8 manifold and such as well. So, yeah. Sorry, E8 manifold comes just from the original one, but there are some other results that Donaldson came up with later, all of which could be put under one rug as the Froshaw invariant has so and so properties.
Okay.
And when was that done? This formalization, this way of looking at it? When was all this done anyway? The whole Instanton form.
So historically, I think in the 80s, Donaldson came up with this Donaldson,
Yes.
like he was looking at that, and Donaldson polynomials or so came about in the late 80s or so, and people were using things about that. So you had structure theorem and stuff like that for it, and which is very close to the advent of Seiberg-Witten theory as well. That's one way where things diverged, and in the other direction, Froshaw's things I think came in the early 2000s or late 90s.
Late 90s.
Yeah,
There's a moment graph, right?
I think so. I'm not sure actually, but
Floer itself was 89.
yeah. Oh right, yeah. How can I talk Floer theory without talking about Floer? So yeah.
Donaldson would be, I think, 83 or 82 or something.
Yeah.
But Floer didn't look at instantons.
Yes,
right?
he did.
Yes, he did. He
Both.
did talk about these Instanton groups.
Both symplectic sphere theory and Instanton sphere theory are due to Floer.
Yeah, within a year apart or something like that.
First was the Arnold conjecture symplectic sphere theory. But the first
Yeah.
paper on Instanton sphere theory is Floer.
So he came up with this, and then, but people still were focusing more on the four-dimensional story, just because that, I mean, it seemed like once you figure out things enough there, then you can transport everything to the three-manifold setting by like adding some boundary conditions everywhere. But then I think the real shift sort of came in when I forget when the real shift actually came about, but like there were already gluing results of sort where you cut along a three torus, what happens and things like that. But those didn't exactly fit in this whole framework because the thing you were cutting along was not nice enough in some sense. So they had to do it by hand. And then I think Froshaw came up with this Froshaw invariant that put most of Donaldson's results about quadratic form, like intersection forms of four manifolds, all under one framework. And then I think after that it became like, okay, this three manifold thing also you can do. You can compute. You can try computing it, and it can give you pretty good things, even just with these issues.
So this was after 2000.
Early 2000s / late 90s, I would say. I think Froshaw also has like two papers or something like that. One where he defines this Froshaw invariant, and the next one where he says that it recovers all of Donaldson's results. But they're all pre-2003, I'm pretty sure.
And what about things like detecting unknowns?
That came in 2008, in fact.
Detecting what?
The unknot.
That is Kronheim or not?
Yeah, that's
So
2008.
that's 2008.
So
It's as late as 2008, is it?
quantum is the unknown detector was definitely 2008.
No, but I'm sorry. Property P is very early.
Yeah, property P is earlier on. It's
Very early.
2003, 4, something like that. So, sorry, what did you?
And that's also Instanton Floer.
Yeah, that's what my next lecture is going to be about. Of these, how do you introduce knots into this framework? So we've talked about fundamental groups of three manifolds. What about knot groups? So like fundamental group of the complement of a knot. How do you analyze them and how do you do things like this for them? Because now, like a lot of this framework, I was talking about R cross Y, right? Now, if Y is already a three manifold with boundary, then this becomes like a four manifold with corners, and that's a priori it's not easy to do the analysis there. And so yeah, but again the key analytic input was again in the 80s when once Donaldson had come up with these polynomial invariants, Cronheim and Roca, when they were trying to figure out structural properties about this, they used these singular instantons, and of course it also had the upshot of the Miller conjecture and the local Thom conjecture that the lowest genus of some homology class that you can get in CP2 is achieved by a curve. Things like that. So all the hard analytic input was there from around then due to Cronheim and Broca, Cliff-Dobbs and others. Yeah. I mean, now I think these days we quote only one or two sources, but there's a whole lot more if you're willing to actually dig through the literature.
Again, the other analytic side, which is what we did to property P, and even now their papers, is the bridge between Seiberg-Witten.
Yeah, the Witten conjecture that predicts that Seiberg-Witten invariants dictate what the Donaldson invariants are and vice versa.
For the
Yes.
property P.
Which is in fact something they proved themselves, I
had
think.
a paper just a few days ago about this, I think.
Yeah.
I've been working on it since the 90s as well as I remember.
Yeah. I think in the symplectic case, Cronheim and Roca already proved it very early on, but like to get it going for everything is like pretty hard analysis, and there is an industry due to Paul Feehan, Thomas Linus, and then I think Yige and Lee also very recently. I mean, that's the only paper I've seen actually so far of trying to go into this stuff. But yeah.
Feehan and Linus is what was in MSRI when there was the rumors of the Cronheim and Roca property P, and that they were building
I
on
see.
the Feehan Linus, which was brand new at that time.
I see. Well, they're still working on it last semester.
Yeah. Well, yeah, but they had enough of it for property P and somewhere in the late.
Yeah, definitely. Like they made the first breakthrough, I think. Not maybe should not be quoted on that, but yeah.